Happy Tuesday. Can everyone hear me? Okay, excellent. Right. What did we do last time? Friday we finished up tangent planes. Right, so we have one more thing left to look at in this unit, the directional derivative. All right, so that is what we're going to look at today. All right. Right, so the idea of a directional derivative, okay, right? So let's say we're sitting on, let's say, some two-dimensional space. Let's just start with that, okay? I'm going to divide this, right? So I'm going to say here's the x-axis. Here's the y-axis, right? And let's say we're starting right in the center. So let's say we're sitting in the center. Doesn't have to be. At some point, let's call that point P. So we already looked at partial x and partial y, right? So partial x is a directional derivative. Specifically, it's a rate of change in the strictly x direction. Right, so strictly along a horizontal line. Partial y, right, would be rate of change in a strictly vertical direction. Right, so along the y-axis in our example. We do this partial x. This here is partial y. But as we examined, right, there's an infinite number of directions just on a plane, not even talking about space. Well, this is the idea of a directional derivative. Right, so I can then go, okay, what is the rate of change as we move in this direction? So that is what we're looking at now. Also, in this section, we introduced a new operator, right? To set my desk, there we go. We introduced what's known as the del operator. What's going on? There we go. Right, it's this upside down delta. Oddly enough, that symbol is the nabla symbol. Right? They call it the del operator, but it's actually nabla, right? Because del, that's del, the partial. Right. And the operator itself depends on the number of dimensions you're working in. Right, so obviously we work in 2 and 3 mostly. So in 2 dimensions, that's how it's defined. In 3 dimensions, it's this. Right, and this now allows us to introduce new operations. We look at only one right now. When we look at vector analysis in a few weeks, we're going to study the other 2. Called the gradient. And I'm just going to write out the 3 spatial dimension one. Right, this is now going to allow us to find directional derivatives. Much easier, in fact. We come back over here. Find the directional derivative, or find the derivative of this function, x squared minus 6y squared, at the point 7, 2 in the direction of, and there's 2 directions, 45 degrees from the positive x, 45 degrees from the negative x. Okay. So the directional derivative. This is important. U needs to be a unit vector. In the direction of f. I should have put at a point P. And this needs to be an F, not a Z. Right, so it's the gradient of your function evaluated at your point dotted with your unit direction vector. And so for both A and B, right, we're going to still need del Z. Right? Partial x partial y evaluate this at the point, right? So the point 7.2, 2 times 7, 14, and then negative 24. And just to make calculations easier, I think we can just factor out a 2. Right, so for part A, call this direction vector U sub A. Right, so we want a unit vector that represents a direction that's 45 degrees from the positive x-axis. Well, wouldn't that just be cosine of 45 and sine of 45? Right? Our directional derivative, gradient of z at the point P dotted with our direction vector. And it'll be 2 times that dot product. Be what? Negative 5 root 2, right? That would be our rate of change at the point at the point, 7, 2, in the direction of an angle 45 degrees to the positive x-axis. For part B, we want 45 degrees from the negative x-axis. Right? So what we're actually looking for is this. Wouldn't that be 135 degrees? Right? We'd wind up with what? Negative root 2 over 2 and root 2 over 2. Right? So it's del z at P dotted with our direction vector. Maybe 2 times the dot product, which is negative here 7 root 2 over 2. What am I doing? Comma minus 12 root 2 over 2. Again, I don't know why I'm thinking this is a vector. It's just parentheses. That would just be what? Negative 19 root 2. Okay. Okay. So what about here? I mean, again, what we're going to need, of course, is the gradient of z. So what would a gradient be for this function? right? So y e to the x, and then you say 1. How'd you get 1? Right? Would just be e to the x, right? Because that is a constant multiple, right? There we go. There's our gradient. Now I evaluate this at our point P, which is 0, 3. Just be 3, 0, right? E to the 0 is 1. Direction vectors. If we're looking at 30 degrees from the positive x-axis, well, that's simple. Cosine of 30 degrees, sine of 30 degrees. For 3 over 2, 1/2. So derivative of z at P in the direction of u sub A, 3, 0, dotted with root 3 over 2, 1/2, which is just, oh, I'm sorry, why did I do 0? Oh dear. E to 0 is 1, not 0. I don't know why I did 0. Fix that up. Be 3 root 3 over 2 plus 1/2, right? Or just 3 root 3 plus 1 all over 2. Direction vector for B. We're at 60 degrees from the negative x-axis. So we're looking at 120 degrees from the positive x-axis, right? So it'd be cosine of 120, sine of 120. Cosine of 120 degrees, negative 1/2, right? And then sine of 120 degrees would be root 3 over 2. Right, that would make our directional derivative 3, 1, dotted with negative 1/2 and root 3 over 2. Right, root 3 minus 3 all over 2. Okay. That looks good. It might be a little bit tough to see, right? But our temperature function T, 64 over x squared plus y squared plus 2. Right. So that's temperature of a heated circular plate at any of its points. Right. The origin obviously being the center of the plate. We're now we're at the point 1, 2 on this plate. We want to find the rate of change of temperature in the direction of pi over 3 from the positive horizontal, right? So if we look at it, that's a pretty good circle. Right, there's the center. We're at some point 1, 2. That'll probably be, I don't know, right about here. Right, we're going in a direction that makes an angle of pi over 3 with respect to the horizontal, right? So what we're going to do is draw an imaginary horizontal line. At our point. Right, and that's the direction that we're going in, right? So that's the derivative we're trying to find in that direction. Right. First thing we need to do, well, actually doesn't have to be the first thing, right? We need the gradient of temperature, right? Two variant, so there's only going to be two components of the gradient. What is the first component? Excuse me. Why is it so laggy? Uh-oh. Video. Frame rate was 29.54. That's not good. Seems to be better now. So it would be the first component of the gradient of temperature. And feel free to unmute yourself to answer the question. That's fine.
I got negative 64 times 2x over x squared plus y squared plus 2 squared.
Is it just the 2 that's being squared there?
No, the entire thing in the denominator.
And then, of course, 64 times negative 2x would be negative 128x. So that's what you got?
Yeah, that's what I got.
I agree. Right, now here's the cool thing. Second component isn't going to be the same, except it's now y instead of x. Being centered there. Right, now we have to evaluate this at our point, which was 1, 2. So that is, you don't have to use quotient rule. That'd be a power chain rule. Okay. Accidentally hung up on myself. It's at the point 1, 2, that first component. Negative. Obviously, the numerator is 128. Denominator, we're going to have 1 squared plus 2 squared, so 1 plus 4. 5 plus 2 is 7, squared is 49. Negative 128 times 2, negative 256, and the denominator is the same, 49. And let's make life easy. Factor out a 128 over 49, and we should be left with 1, 2. Direction vector. It was making an angle of pi over 3 from the positive horizontal, right? Well, that's easy then, right? It's just going to be cosine of pi over 3 sine of pi over 3. To be 1/2 root 3 over 2. Which again, we can actually simplify by saying it's a half times 1 root 3. Rate of change. Going to be this. Dotted with now our unit vector. Negative 128 over 49 times the half would be negative 64 over 49. Now we just take the dot product of the vectors. Be 1 plus 2 root 3. Right, so this is our rate of change in that direction of temperature. Right? Units would be the same. Right, so it would be units of temperature per units of direction. The units of the magnitude of direction, right? So if temperature was Kelvin, we'll say direction, the magnitudes in meters. This would be Kelvin per meter. Right. Electrical potential at any point xy is given by log of the square root of x squared plus y squared. We want to find the rate of change of our electrical potential at the 0.34 in the direction toward the 0.26. I think this might be more beneficial to write it this way. All right, so remember laws of logarithms, right? So that's all that we're doing here. I think this is definitely beneficial for us. Now I want the gradient. Well, it'd be this 1/2 times now the derivative with respect to x of the log of x squared plus y squared. And remember, derivative of log of u u prime over u, right? So it would be 2x over the x squared plus y squared. And that can simplify, which I'm going to write it right now. That's just x over x squared plus y squared. And then obviously you should easily be able to see that with respect to y, you get a similar term. Just be y over x squared plus y squared. Okay? We now want that evaluated at the point 3, 4. So it'll be what? 9 and 16 is 25. So we get what? 3/25 and 4/25? And let's factor out that 1/25. Just write it as then 1/25 times the vector 3, 4. We now need a direction vector. Well, direction. We're starting at the point 3, 4. Right? That's our starting point. We want to go towards the point 2, 6. So if this is point P, call that point Q. The direction would be that line segment, wouldn't it? Two minus 3, -1. 6 minus 4, 2. There is our direction. Okay, but here's the thing. That's not unit. So we normalize it. One over root 5 times the vector -1, 2. Now it is unit vector. Right, then our derivative of our electric potential at the point 3, 4 in the direction towards the point 2, 6. 1/25 times the vector 3, 4 dotted with 1 over root 5 times the vector -1, 2. And we get 1 over 5 root 5.
Professor, I have a question. For
Yes.
you, where did you get the 1 over square root of 5?
So do you remember how to normalize vectors? Remember how we did that?
Yes.
That's what we did, right? It's 1 over the magnitude of the vector
Okay.
times the vector. So what is the magnitude of this vector?
It would just be square root of -1, or no, I'm not sorry. -1 squared plus 2 squared over the square, or in square root, right?
Right. So
Okay.
1 plus 4, 5, right?
Yes.
And then square root. So that's where the 1 over root 5 came from.
Okay, awesome. Thank you.
Right, because remember, it's 1 over that length. Okay. That answered that. Perfect. And so again, our rate of change would be 1 over 5 root 5, and then the units would be whatever the unit of the potential would be, of the electric potential. I actually don't remember what that is off the top of my head. Per units of the magnitude of the direction vector, probably be like meters or something. Yes, this one, okay. I find the derivative of the function xy plus 2xz minus y squared plus z squared at the point 1, -2, 1 along the curve given by r equals t minus 2, t squared in the direction of increasing z. Let's first find the gradient of f. Right, well, this is now a 3-variate function, right? So we're going to have three components to the gradient. First component, partial with respect to x. Y plus 2z. Second component would be the partial with respect to y. So it could be x minus 2y. Third component, partial with respect to z. Two x plus 2z. Evaluate that at the point 1, -2, 1. And what do we get? -2 plus 2 is 0. 1 plus 4 is 5. It looks like 2 plus 2 is 4. All right, so that would be our gradient. At 1, -2, 1. Okay, so now we need a direction. Right. Specifically, we want the direction of increasing z along this curve. So we want r prime. Now remember, we're already at the point 1, negative 2, 1. What value of t, when you plug it into r of t, gives you, hold on, wait. I think that's a typo. I actually think this is supposed to be t minus 3. All right. So what value of t when plugged into this r of t, which should have been t minus 3, t squared, gives you 1, negative 2, 1. T equals 1. Since that is the point we're starting at, let's go r prime of 1. Notice that that satisfies our condition of an increasing z, right? Because the z component is positive 2, meaning it is increasing. So we're going to take that as our direction. Now we just need a unit vector that represents that direction. All right, so 1 over root 6 times 1, 1, 2. It's big F, right? Capital F. One, negative 2, 1. Okay. Zero, 5, 4 dotted with 1 over the square root of 6 times 1, 1, 2. 0, we get 5 plus 8. So our directional derivative 13 over root 6. 2. Click. Any questions so far? Next, that's going to, in this case here, show us the direction of increasing z, right? Because that's what a derivative gives you, right? Rate of change. Anything else? Okay. So here's how the quiz is going to work. I just posted a link in chat to a Microsoft form. This form has as the question a picture of the actual question from the quiz. There's a 15-minute time limit on it. Once you start it, I would recommend that you save the last 5 minutes, take a picture of your work, and upload that picture onto the form. This form closes at 11 o'clock. Right, so you're just going to do the quiz on loose leaf paper, take a picture of it, and upload the image. It doesn't matter the file type, JPEG, PDF, whatever. Right, so go ahead and do that. At 11 o'clock, when the form closes, I will just print out all the results. Yeah, so once you take the picture, you're going to upload it onto the form because the form's question is a file upload. Right, I'll then print out the results. And then when I grade them, just hand back what I printed out. What I can also do is provide, hope this works. If you want to upload the picture right from your phone, oops, downloads. There we go. There is a QR code. Right, so if you just have the picture on your phone, you just want to upload it directly from your phone, you can take a picture of that QR code and do it right on your phone. So either one.